Cool. Okay, so hello everyone. My name is Vincent Grandin, and I did this work together with Professor François Pomerleau. And
hold on, I don't think we're sharing it. Or were we sharing it?
Before we were.
I don't think we are over here. Sorry. They would yell at us out there. Yeah. Also try to keep this open. All right, I think we're good. Thank you. Sorry.
Yeah, so I did this work together with Professor François Pomerleau and Professor Philippe Giga. In our work, we explore how deep learning algorithms behave in harsh synthetic forest environments. And first, let me tell you why we did it on synthetic images instead of real-world image. So initially, we planned a perception system capable of detecting trees for autonomous tree felling operation. So the system will detect the trees along with the estimated felling cut. This system will be based on a deep learning algorithm, which is a data-centric approach that requires a sufficient number of annotated images to learn from. These annotations can take multiple forms. So as we can see here, we can have bounding box, segmentation mask, key points, or a combination of them. Since creating an image dataset is a cumbersome process, we want to be sure that the annotations we're going to use are going to be worth it. So when we looked at previous methods, we saw that we were not the only one asking ourselves these questions. In fact, all previous methods use different annotation types. For instance, in 2021, Daselva used bounding box over trunk. In 2020, Itakura used bounding box over trees. And in 2019, Liu used segmentation mask on. So as you can see, there's no clear consensus about which annotations are preferable. In this context, the goal of our research was three things to identify. The first one was which modality is the most important between RGB and depth. Secondly, which annotations are the most important? Will bounding box be enough, or should we add segmentation mask? And lastly, what kind of performance should we expect from deep learning in forest environments? To answer these questions, we propose to benchmark mask RCNN on a large, densely annotated synthetic dataset. The benchmark will be on a large dataset, and this will allow us to fill the data gap and avoid hand annotations while also including as many realistic conditions as possible. The dataset can later on serve for pre-training before eventually fine-tuning on real-world image. So to create our dataset, we developed a simulator based on the Unity game engine to render realistic forest scenes. We configured it to procedurally terraform the terrain, texture it, and spawn objects on it. The forest density is controlled through various spawn rules, such as the altitude, the terrain slope, and the object density in a given area. We use 17 different tree models, along with various shrubs, branches, stumps, and grass model. The objects are then spawned with various size and proportions to increase scene diversity. And as we can see on the figure on the right, we can also modify the lighting conditions to simulate morning, day, evening, and night. And we can also add weather effect like rain, fog, and snow. From each scenes, depending on its size, we collect between 200 to 1,000 images and autonomously annotate them. An early finding we did was that including the entire trees in the bounding box can lead to misdetection. So as we can see on the image on the left, the two trees at the front have their ground truth bounding box overlapping. And when a model like MaskRCN makes a prediction, the non-maximum operation will suppress one of the two predicted bounding box so that only one tree is detected. So instead of detecting the entire tree, we propose to only detect the trunk region. In addition to the bounding box and the segmentation mask, we also included 5 key points per tree. So we have 2 for the diameter, 1 for the felling cut, and 2 for the tree axis. Only trees within 10 meters from the camera are annotated, which correspond to approximately the reach of a real harvester. And so all the annotations you see on the right are the ones we use in all our experiments. So with that, we generated over 43,000 images and 162 annotations, and we called our dataset SIGN-Tree43K. Here are some samples from the dataset. Our mask RCN model will take these images as input and pass it through a backbone, which is, in our case, ResNet 50, ResNet 101, or ResNext 101. And the model heads will then estimate the class, the bounding box, the segmentation mask, and the key points, as we can see on the output image. To predict the key points, we adapted the key point RCN model architecture that is usually used for human pose estimation by reducing the number of predicted key points from 17 to 5. So the training details, we train all our models on the Coco person dataset, and we freeze the 2 first convolutional layers of the backbone. The dataset we split into 3 subsets. So we put 40,000 images in the train set, 1,000 in the validation, and 2,000 in the test set. To improve the model generalization and reduce overfitting, we employed common data augmentation techniques such as image resizing, flipping, shearing, etc. No data augmentation is used as at validation or test time. So now we can move on to the results. One of our goals was to assess which is the most important promising modality between depth and RGB. So we trained our model on both and compared. From the result obtained, apart from the first metric in blue, there's no clear distinction between RGB and depth for the segmentation task, and a little distinction for the average bounding box 50 as seen in yellow. In fact, it's only for the average bounding box precision in blue that we observe a big increase in favor of depth by 9.42%. This only means that on average, and for an intersection over union between 50 and 95%, the bounding box are better localized on depth image. But in our case, the main metric we focus on is the yellow one, because it considers detection as good when 50% or more of the IOU is corresponding with the ground truth. So even if the trees are not perfectly centered in the bounding box, it's not a big deal as long as we detect it. Concerning depth image, we want to outline the difference when using real-life sensor versus synthetic. So while synthetic images are near perfect, we see that the depth camera cannot yet capture that much level of information and with that much precision. So as we saw on the right, the depth image we took using a Z camera under good lighting condition still suffers from rough edges and undefined object shape. So this, when we use this for prediction on real images, it could be detrimental. So that's dangerous. To evaluate whether the mask or key points annotation should be included in the dataset, we ran a multitask learning experiment. We keep the class and bounding box branch as seen on top, but we disable either the mask or key points as seen in pale. Interestingly, and similar to other previous works, we observed that adding the segmentation task improves detection result for all tasks, but that adding the key point branch does not really benefit any other task. This indicates that better bounding box and key points prediction can occur by learning features specific to segmentation. And to us, this indicates that including the segmentation annotation in the dataset is primordial. So the key points prediction are a big part of our study. And here's an example of a use case where a harvester is in front of a bunch of trees. So even if we detect the bounding box and the segmentation mask, it doesn't really help to know where to grasp it. But with key points, the operator have all the information necessary to go grasp it with at the proper height, at the proper angle, and the proper grasper width. But to do that, the key point must be accurate, especially for the fading cut estimation, as seen with the red arrow. So when we look at its localization error, we see that there's a bigger error vertically, about 3 times the error that we have horizontally. And intuitively, this was to be expected because predicting the key point height requires global image information, while predicting the key points centering or edge requires more local information in the image. From a practical standpoint, we prefer a small horizontal error because it can lead to fading cut estimation being beside the tree. And with the vertical error, if it's too high, it's not a big deal because the harvester can just grasp it and roll down the tree. In our last experiment, we qualitatively assessed how well the features learned on synthetic images transfer to real-world image. These video segments were filmed by us in a Canadian forest with a Z stereo camera. As we can see, our mask Gaussian model can detect trees without any fine-tuning on real images. And we observe also 2 flaws, is that some trees seem to be detected further than 10 meters away, and that the network has a low recall rate, so it misses trees that are too different from the one in the simulation. But this transferability is, however, very promising because it could achieve state-of-the-art performance when we fine-tune it on real image. In our current work, we did the creation of a small dataset of RGB and depth image, and using this image, we plan on, we already tried it, to transfer it on real image via fine-tuning, and we saw that pre-training on the synthetic dataset really helps the learning and the results. And in the future works, we plan on using semi-supervised or self-supervised learning methods to improve the results. And when the trees when the detection is good, the next logical step will be tracking. So in conclusion, although a synthetic dataset cannot completely replace real-world data, multiple works demonstrate that it's a cost-effective method that offers good transferability. Our experiments on synthetic images shows that the RGB and depth can achieve similar performance, that the segmentation mask is worth annotating, or at least in simulation, because in real life it costs a lot of money, that key points seem accurate enough for autonomous tree felling, and finally that simulation is worth it. It generalized partially to real images, which kinds of fill the data gap that we have currently. And all our models are available on the GitHub of our project, so Percept3 V1. So now thank you for listening, and 5 minutes queue.
Are there any questions? One?
Nice work, Vincent. Apart that trunks, have you labeled any other classes in the images?
No. But yeah, it will be interesting to label the species.
Yeah.
Yeah, that could lead to even to precision forestry in the end.
Yeah, that was my guess.
I also have a question. So Vincent, you recognize in your presentation that there's a gap between depth data
Yeah.
from the simulator and real depth data, which is obvious. My question is, I didn't understand if you model that, because the transferability of these approaches is as good as the environment and the sensor. So the environment needs to be as close as reality, and the sensor also needs to be as close as the real sensor. And most of the time, we are concerned with illumination, which was talked a while ago, lighting, and so on, as Paulo addressed. But most of the time, we don't consider these effects on the sensor itself.
Yeah.
So because there's the illumination, the difference that it causes in an object, and there's also the difference that it causes in the sensor itself, as heat and other kind of things. Is it on your plans, on your roadmap, to try to make these sensors get closer to reality, or not?
Well, when we use data augmentation, it kind of does that in a way. But no, we didn't really simulate. Well, what I mean is we didn't reduce the quality of our synthetic depth image, but maybe we should try it with reducing it so it could eventually prove it when we use real life sensor. And what would be interesting if we could really use depth image is that you can, after that, you can transfer from forest to forest, and you don't have the domain adaptation problem because your depth image, they're kind of proof to that. So.
But by the way, just a curiosity, the results you showed in the end were with RGB only, or RGB and depth?
It's RGB on.
RGB only.
Because when we tried it on real for the depth image, it's very bad.
Okay.
Yeah, there's nothing detected without fine tuning. So
Okay.
so that's why we put the warning to, in simulation it performs well, but when you use real life sensor, there's a stop there.
Yeah. Okay.
Great talk. I was curious, you're talking about like fine tuning your model on real data that's annotated. I was wondering if you could go the other way and make your simulator look more realistic with unannotated real data. So maybe you change the lighting so it's more realistic, or even like improve the quality of your assets.
Yes, that's a nice, it will be a good way to do it. But I think we're leaving the simulator as it is, and instead we're gonna focus on training with unlabeled images. So self-supervised learning with vision transformers seems very attractive to us from what we've seen in recent studies. But yeah, that's definitely a way to do it.
Okay, thank you.